So in this lesson, we'll be looking at some more theory having to do with thermochemistry. We'll look at the Gibbs free energy equation, and then after that we'll be looking at reaction energy diagrams. The Gibbs free energy equation is used for determining when a reaction or physical process is spontaneous. The reaction energy diagrams are used for let's not go that far. In this lesson, we'll be covering more theory having to do with thermochemistry. We'll look at the Gibbs free energy equation, which helps us determine when a process is spontaneous. And we'll look at reaction energy diagrams. Now, this lesson best follows in order behind the two previous lessons on thermochemistry: heat energy transfer calculations and calorimetry calculations. We're going to talk about something called the Gibbs free energy equation. And the purpose of Gibbs free energy is to figure out when a process is spontaneous. Okay? That's really the key here. When is a chemical process spontaneous? All right? Physical changes can be predicted the same way. Physical or chemical changes can be predicted to be spontaneous based on the Gibbs free energy equation. So, what does spontaneous mean? Spontaneous means that the process takes place without any additional outside influences. You don't change the conditions, and it'll happen anyway without any additional help. So if you need a definition, hint, hint, spontaneous is a process that will happen on its own without any additional outside changes or influence. Okay? So that's what spontaneous means. You've probably used the term spontaneous referring to people. You know, that person's really spontaneous, meaning like they just, they react quickly to almost anything, and they kind of, tend to say their mind, they laugh easily, and they get angry easily and stuff like that. That's a spontaneous person. All right? Huh? I thought you were saying something. No? Okay. All right. So we're talking about Gibbs free energy. And the Gibbs free energy equation, well, what it does is help us predict when a process is spontaneous. Okay? Now, you can do math with a Gibbs free energy equation, but that's not the way that we're going to use it, and it's not the way that, most often, even in college chemistry, it's used. Most of the time, we look at it and we make generalized predictions based on that equation. But I want to be clear about what spontaneity means. Just because a process is thermodynamically spontaneous, okay, just because a process is thermodynamically spontaneous does not mean that it will happen on its own. An example is this, that diamonds, which are pure carbon, are not thermodynamically stable. If you were to take the values for diamonds and plug it into the Gibbs free energy equation, it would tell you that the decay of diamonds into graphite is a thermodynamically preferred process, meaning it's spontaneous. But nobody in here has ever seen a diamond decay, right? In fact, the phrase they used to use to sell diamonds, for jewelry stores, diamonds are forever. Okay? Well, actually, they're not forever, but there's another process we'll talk about later that has to be involved in figuring out whether it is going to happen. It might be spontaneous for it to decay. That does not mean that it's actually going to decay in our lifetimes or your grandchildren's lifetimes or all of your progeny's lifetimes till the sun explodes and engulfs the earth and everybody's dead. So, I know that's kind of gross, isn't it? Anyway, here's the equation, all right? So this right here is the term for the change in Gibbs free energy. Remember, the delta symbol, the Greek letter delta is a triangle, or the capital letter D, or delta, is a triangle. That means the change in Gibbs free energy, okay? And if Gibbs free energy is equal to delta H. Now, you've seen delta H already. Okay. Oh. All right, so you've seen this before. This is enthalpy, and so this is the change in enthalpy. We've used that already. And this, while it is more complex than the definition I give you, for high school chemistry, you can think of delta H as the amount of stored energy. So when I say delta H, it means the change in stored energy. So as the process goes from the beginning to the end, either from the physical state at the beginning to the ending state in the physical change, or in a chemical reaction, it's the beginning reactants to the ending products, that change in the amount of stored heat energy is considered delta H. All right, it's a bit more complex than that, but for high school chemistry, and probably most of college chemistry, at least in the earlier years, it'll serve you quite well. Okay? And then minus temperature. Now it has to be absolute temperature, so this has to be in Kelvin. All right? There are several different temperature scales. The one we don't use is Fahrenheit. One we use in lab a lot is the Celsius scale, and that's a practical way because of the way the thermometers are set up. It's easier to read that way. But the most practical of all the, as far as the math is concerned, all the temperature scales, is the Kelvin scale. It starts at absolute zero. So 0 on the Kelvin scale is absolute zero. Okay? And absolute zero is negative 273.15 degrees on the Celsius scale. Okay? Really, really cold. At absolute zero, all motion of everything stops. Even the movement of electrons and protons and the subproton and subneutron particles. They all stop.
What would that be on the Fahrenheit scale?
I do not know what it is on the Fahrenheit scale, but it's in the neighborhood of negative 600, something like that. Okay, I don't know. I may be way off. Okay, look it up. All right, and then we've got this last term, so that's the temperature times delta S. Okay. So we said this is the change in Gibbs free energy. And this is the change, for us anyway, change in stored heat energy. This is the temperature on the absolute scale, or the Kelvin scale. Absolute or Kelvin scale.
And Mr. Sack,
Yeah.
it would be negative 460 degrees.
There you go. And then the delta S term, this is the change in, and by the way, this term is enthalpy. This is the change in entropy. So we've got enthalpy and entropy. And entropy is a measure of disorder. So let me give you kind of a general idea, and it is a general idea, of entropy, okay? How many of you are really good about keeping your rooms neat and clean and tidy? 1, 2, 3, 4, 5, 6, 7, 8, about 8 kids out of the whole 20-something kids in the room, okay? So the rest of you probably, if I visited your bedroom, I'd see it very messy, right? All right. All right. So if your bedroom tends to be messy, that's disorder. If you tend to keep your room clean and tidy, that's order, okay? The more disordered it is, the larger the S term is. Does that make sense?
Yeah.
So let's say that Mom cleaned up your room. It's spick and span, everything's put away, everything's neat and tidy, and over the weekend you get it to be a total wreck. Okay, your bed's not made, all the stuff you have in your room is everywhere. I started to say toys, but high school students don't have toys, do you? Well, video games, I guess. But anyway, everything's scattered around. Well, that means that the change in disorder increased. So entropy increased over the period of the weekend, right? All right, now, think of disorder then in terms of molecules and atoms. All right? The more disordered they are, the more disarranged or unarranged or poorly arranged they are, the greater the disorder. So if I have an ice cube, all right, I've frozen some water, I've got an ice cube, and I leave it out on the kitchen counter and it melts. Those molecules that make up that ice cube have gone from being stuck together nice and tight and tightly arranged to being disordered and all around, right?
Yeah.
That means that the delta S term increased while it was melting. Does that make sense? Okay. If I have a chemical reaction, and over the process of that chemical reaction I end up with more molecules than I started with, that's more disordered. You with me? If I heat up something, the particles that make up that thing are moving around faster when the temperature goes up. A higher temperature means more disorder within that substance. That makes sense? So just think of it in terms of the particles moving around and what it means. Now that means you got to kind of, you got to theorize a little bit. Okay, you got to use that brain to imagine what's happening. The phrase that I often use is you got to let the movie in your head run. Okay, you got to watch the movie in your head and think about what's happening. Okay, so what does the movie in your head tell you is happening? Now, if you're not imaginative, then you're going to have trouble with this. So you got to imagine things. All right, chemistry is a very creative subject. You got a question?
No, I was just like, when you say to live in your head, is you like daydreaming and stuff?
Yeah, it's kind of like purposeful daydreaming. You're purposely thinking about what are those molecules actually doing inside that ice cube, or when that chemical reaction occurs. Okay? All right. So let's use these terms, and here's the thing. A process is considered to be spontaneous when the change in Gibbs free energy is negative. A process is considered to be spontaneous when the change in Gibbs free energy is negative. Okay? If the Gibbs free energy is zero, or if the Gibbs free energy change rather is zero, or the Gibbs free energy change is positive, it's not spontaneous. Okay? So you might have to change the conditions to make it happen. You can still make it happen, but it just means you've got to work with it and change some things to make it happen. Okay? So let's look at the ice cube example. Okay? Just for right now. All right? So for an ice cube, now I hope you wrote down that a process is spontaneous when change in Gibbs free energy is negative. It's spontaneous when the change in Gibbs free energy is negative. Okay? Let's look at the process of an ice cube melting. Okay? The question is, for delta H, is that going to be a positive number or a negative number? Now, remember, that's a stored energy. Okay? Stored energy in the heat energy, actually. Okay? Is the stored energy in liquid water greater or less than the frozen water? Yes. You think it's the liquid water is less than, or the liquid water is more than? Yeah, you've got more heat in the liquid water because that's what it takes. Remember the graph that we looked at yesterday? And we said that as you add more heat energy to something, it increases the temperature. So conversely then, as the temperature goes up, then the heat energy is also going up. So here's our graph we looked at yesterday. As the heat energy increases, so does the temperature. So if the temperature is higher, the heat energy is higher. Make sense?
Yeah.
All right. So we've got more heat energy in the water when it's liquid as opposed to when it's solid. So this is a positive number. We don't know how much the number is, but we at least know it's positive, right? Okay. Then we've got the temperature here. All right. Is the temperature, relatively speaking, positive? That is to say, is it a fairly high number or is it a fairly low number? For liquid water? Or for melting water, is it liquid? I would say it's fairly neutral. It's not really changing up or down too much. Does that make sense? So we can say it's positive, but it's not very positive. It's just kind of positive, okay? I can make that a little tiny plus sign if I want to. All right? It's not really, really cold, but it's not really, really hot either. We're just melting water. Okay? Let's look at the delta S term then. Is liquid water more disordered or less disordered than solid or ice? More disordered. So it changed and went up. The amount of disorder went up. That makes sense? Okay. Now, remember we've got a negative or a minus right here. Okay? So let's look and imagine what's going to happen. All right. Now, here's a hint to you that'll help you. Delta H is almost always, not always, but almost always a larger number than delta S is, if that'll help you. Okay? All right. So if this is a positive number and temperature, which is just barely positive, kind of positive, is multiplied times a positive delta S, then this part of the equation is going to be positive. A positive number times a positive number gives you a positive number, right? All right. So we're taking a positive number and we're subtracting a positive number. All right. Under what conditions then is the overall equation going to be negative? Huh? It'll be positive if temperature is large enough. Okay? If this is a fairly large number, and that's going to be usually a smaller number than delta H, then the T multiplied by the delta S will overcome this positive, because this is negative right here. Right? So if I have negative here, and T is, the larger T gets, delta S is always positive. The larger T gets, the more that all of this right here becomes negative, and a positive number minus some other number is going to be negative if T gets big enough. That makes sense? Therefore, delta G is negative, but it's only if T is large enough. Does that make sense? You don't have to know whether it's large enough, because you don't have to make a prediction that it will happen or won't happen. What you would say here is, okay, this is spontaneous if T is large enough. That's all you got to say. That makes sense? All right. Let's look then at what happens when we are, and I'm trying to use some simple examples that you're all familiar with, that we have steam condensing. And we're going to assume we have room temperature, okay? Now what I want you to do is to do the same thing I just did with all these terms, discuss it with a neighbor, and try and figure out whether steam condensing is going to be a spontaneous process at room temperature or not a spontaneous process at room temperature, okay? So we'll come back together here in a minute and take a look at what findings you have, all right? So try to figure out for yourself, based on these terms here, whether steam condensing at room temperature is going to be a spontaneous process or not going to be a spontaneous process. Do you think that, what about the delta H term? Is it going to be a positive or negative term? Okay, so as the temperature goes down, or as you condense the steam, remember steam is gas particles, and the water molecules are spread way apart in a gas, okay? Well, when it becomes a liquid, they're touching, but they're still kind of moving around each other. And so the amount of stored energy here in the steam is higher, and as you go to liquid, the amount of heat energy stored in it is lower. Okay? Those particles moving faster and spread way out, that's a higher amount of stored energy than when they become a liquid. So since we're going from gas to liquid, this is going to be a negative number. Right? All right. What about the temperature? Okay, so it's positive, it's kind of neutral, pretty, not really, really high. Okay, what about delta S? Are we becoming less? Positive delta S. Okay, so remember, gas particles are moving way around each other, moving really fast. Liquid particles are moving a little bit slower and touching each other. You think that's more disordered?
No.
You see what I'm saying? So that's going to be a negative term. All right, so we've got this negative term here. times these two things, right? These are multiplied times each other. All right, so a negative minus a negative. Well, when you have this times that, temperatures being positive, that's being delta S, this overall term is negative. Okay? So we have a negative term minus a negative term. Now, a negative term times a negative term means that's positive, right? All right, so those two together make that positive. Okay. Now we've got this minus term and this positive term. So when is this going to be spontaneous? Only if this is small enough? Huh? Large enough. Okay. So this plus times a negative, a positive term times a negative term gives you a negative term, and we're subtracting a negative term. So it's like saying this negative is multiplied times that positive, right? Okay? And you're saying that this is going to be negative being spontaneous if this is a large number. I'm saying this takes over. Huh? You've got to have this term being larger than that number. Okay, for it to be negative. So this is negative if the change in enthalpy is large enough. Now, let's take a second and look at how much enthalpy there is, change in enthalpy, when we're changing steam into liquid water. What is that number? We actually have a number for changing steam into water. What is the delta H for changing steam into water, into liquid water? Huh? 2260, 2,260 joules per gram. That's a pretty large delta H. Okay, we talked about that this week, that steam, the changing from liquid water into steam has a huge delta H. Okay, so this term right here is almost always a big number. That makes sense? So it makes it, most of the time, this is going to be spontaneous if the temperature doesn't get to be too big. Now here's the thing. If this temperature number gets really big, then this term gets too big. Does that make sense? So that makes sense too if you think about it. Temperature gets over 100 degrees, it's not going to condense. See what I'm saying? Got it? Now these are a couple of processes that you're familiar with. What if we were to apply this now to something for which you are not familiar? Okay, let's see if we can use that. Okay, let's take the electrolysis of water. So the electrolysis of water works like this. We have liquid water, okay, and we're going to, actually you have to put salt in it of some kind, or acid in it to cause it to conduct electricity, and we have to put electricity in it. And electricity is a form of energy. And when we do that, we break the water up into gas that is hydrogen gas and gas that is oxygen gas. Now, in physical science, you learn to balance equations by inspection. We'll learn a new process in the class, but we haven't gotten there yet. But you should be able to figure out how to balance this equation. What coefficients do I need in front of these numbers to balance this equation? Well, I've got two oxygens over here. How do I have two oxygens on the left side? Well, y'all did this in physical science now. How do you balance this equation?
I got you.
Put a 2 here. Okay. Is it balanced now? I have 4 hydrogens on the left now. Now the equation's balanced. All right, so here's what we're doing. We're putting energy into the system. All right? Remember we talked about systems and surroundings yesterday? This is our system. All right? This whole process here. All the chemicals and the changes going on is part of our system. Okay? We're putting energy into it to get this to happen. So as we go from this to this side has more stored energy than this. That makes sense?
Yeah.
Therefore, delta H is going to be positive or negative. Okay? So delta H, we already know, is a positive term. All right. The temperature doesn't have to be particularly high. We can say it's just kind of an average plus. Okay? And what about the change in entropy? Are we becoming more disordered or less disordered? All right, you're saying more. Why would you say more?
Wait, no, it's good.
You might be right. I'm just asking. You don't assume because I'm asking you the question that I think you're wrong. I'm asking you the question to get you to justify your answer. Can anybody tell me whether they think it is more disordered as they go from this side to this side or less disordered? All right, you're saying less as you go from here to here? Okay. Anybody disagree with that? You disagree? Why do you think it's more disordered? Why?
Because it's more oxygen.
More oxygen. Okay. Well, let me help you out here just a little bit. Okay. It's the number of particles that matter, not what the nature of those particles are. Except there's a difference between liquid and gas. We just talked about that, right? We said steam is more disordered than a liquid is because the particles are moving faster and they're further apart. Okay? Now, does that revise your answer any? Does that help you out any? Yeah, that means gas. Well, oxygen is a gas, right? I mean, you have to get oxygen really, really cold to get it to be a liquid. What do you think? You're saying more now, and you're saying less. All right. So, what do you think? Go ahead. Huh? You think it's more disordered? Why? Justify your answer. Remember, claim, evidence, reasoning? You've got to remember that. The claim is it's more disordered. The evidence is found here somewhere. You've got to explain it. And then you have reasoning to explain why. Okay, so tell me, in claim, evidence, reasoning, why you think it's more disordered.
Because a gas has the particles are moving more.
Okay, we got gases. The particles are further apart, moving faster. All right, there is an evidence and reasoning part of it. Okay, is there anything else?
In the liquid form, they're still moving, but they're not moving as far apart.
Okay, that's further explanation of the same thing. Liquid forms are moving a little bit slower. They're touching each other. They're more ordered, so we're getting more disorder going to this side. Is there anything else? Because there may be multiple things involved here. All right, there is another reason why it's more disordered. Not only are we going from liquid to gas, we have more particles over here than we have over here. More particles means more disorder.
Yeah.
Okay? So our delta S term is increasing, right? So is our delta S term going to be a positive for increasing or a negative for decreasing? Positive. All right, now, so what we have here is a positive term, and a positive times a positive gives me a positive. So we're having a positive minus a positive. Okay? Under what conditions is this going to be negative and therefore spontaneous? If the temperature is large enough or the entropy is large enough. Either one will make it large enough, right?
Yeah.
Okay? Temperature's pretty average. We're not going to change that. You can do this at low temperatures or high temperatures. Get the same thing. I know you guys don't know that yet. So really it's dependent on the amount of disorder. Okay? And that's kind of a lot of disorder here. All right? Not only do we have gases, but we have more particles. That's a pretty large delta S. Okay? So this is going to be, and we're adding energy to the system as long as we're adding energy. It won't happen on its own because if we don't add energy to the system, delta H is not going to be positive. Does that make sense? Are you with me there? Unless we add electricity to the system, delta H is not going to be positive. Well, you wouldn't know whether it is or not, actually. But it's because we added electricity to the system, you know that delta H is positive. So as long as the disorder is big enough, then delta G is going to be negative. Okay? So this is negative and therefore spontaneous. Okay, so negative and therefore spontaneous if the disorder is greater than the heat energy added to the system. Now, I know we're adding electricity, not heat, but one form of energy can be transformed into another. Okay, and I know that's a little bit something beyond what we've talked about so far in here, but that really is something you've studied in other science classes. Okay, different types of energy can be changed into other types of energy. And enthalpy, while we're using it to say heat energy, really means all forms of energy. Okay, you with me? All right. Does that make sense to you? No. You don't understand why this is positive? Oh, okay. It's negative if this part. All right. Let's do this. Try to take this out a little bit further. This is a positive term minus a positive term. So in order for this process to be negative, this second positive term must be bigger than this first positive term, right? Make sense? Since the temperature is not going to change, the only thing that's going to make this more positive is if delta S is bigger. You with me? So the only thing affecting the fact that the second term, this combined term here is bigger than this first term is if delta S is bigger. Therefore, it's spontaneous if the disorder, this term right here, this delta S term, is greater than the heat energy we're adding right here. See what I'm saying?
Yeah.
Claim, evidence, reasoning. Okay, got it? Now look, I'm gonna tell you something that may blow your mind here because you're used to either answers being right or wrong. You can give me a wrong answer and justify it reasonably and still get full credit for the answer. If your answer stands up to scrutiny, claim, evidence, reasoning, then it's possible to get full credit for an answer even though your answer is technically wrong. All right? In the sciences, it's important that you follow this process. What is the main goal of science, guys? Remember that? Yeah. Unit 1. What's the main goal of science?
Figure out how the universe works.
Not just figuring out how the universe works, but coming up with defendable arguments. So if your argument stands up to a defense, I mean, if you have a solid defense of your argument, and of course that's my judgment, all right? It has to be based on the science that you should know. You can't just make up stuff, okay? If you have a defendable argument for something like this, you can get full credit even though your answer's wrong. You with me? Yeah. All right? It's kind of like in if you were taking a debate class. You win the debate based on your argument, not whether you're right. All right? Now, in science, the debate has to be based on sound science. So what's already known about the science that you would know. I don't expect you to know what I know. I expect you to know the stuff you've been taught in 5th grade and 9th grade and so forth. And I keep referring to 5th grade because that's the elementary grade in which you have the most chemistry. Okay? You with me? Make sense? So that's a different way of thinking about things. This is like a math class. It's either right or wrong. Okay? Sometimes you can be wrong and still be right. Okay? If you have a reasonable argument. Because science is tentative. We talked about that too. Right? Science, we say, this is the reason why something happens, but if we have new evidence to contradict that, we got to revise that argument. We got to come up with maybe a different argument. You with me? And that's what I want you to think about, how I want you to think about science. That in some things, you can be right in terms of getting all the credit for it, and still be technically wrong. Got it? That's a whole different way of thinking about things. Now, there are some things you're either right or wrong about. When you're doing dimensional analysis, yeah, it's either set up right or it's not set up right. Okay, you got the right answer, you don't have the right answer. All right, those things there's not any question about that. But for things like this, sometimes you can be wrong and still be right, in a sense. All right, I know you're not used to that, but I want you to start getting used to that because guess what? When you go to college, that's what you're going to be doing there too. All right?
Alright. Go to my art class and might listen. This might not look good, but it is.
Some of the stuff that we call good art today would have been called garbage 200 years ago. So I don't know. I mean, art maybe it works the same way too. All right. 20, 30 years ago, if somebody painted a picture on the side of a building, with spray paint, they would have called it vandalism, without question. But there's some of that stuff they paint on the sides of buildings is pretty good art, and so there's kind of a new appreciation for that. So views change on those kind of things, even in art. Okay. So let's talk about some of the things then that we kind of in passing mentioned with the diamond argument. We said that diamonds decaying are spontaneous. Okay, it is a spontaneous process for diamonds to decay, but they don't. And so we're going to look at we're going to look at the part of science that deals with why that is the case. Okay, so again, we're doing some theory here. All right. So what I'm going to give you is, these are called reaction energy diagrams. Reaction energy diagrams. So this is talking about reaction energy. So a moment ago we were looking at the equation where we had water being changed into hydrogen gas and oxygen gas. We're talking about the energy being added to it, okay? The question is about what happens with the energy over the whole process of this reaction, okay? As we go from the beginning to the ending, what's happening with the energy overall within the system? Now that's different than what's happening outside the system. I might be putting electricity into this system, but some of that electricity is being lost to heat, so it's not really doing anything. It's only we're talking about the energy that's happening inside where the atoms and molecules are located. What's happening in the reaction itself. Okay? Now that's kind of a difficult thing for some students to grasp. We're not just talking about any energy. We're only talking about the energy that is happening or going on or changing within the system we're looking at. Okay? So you got to, again, run that movie in your head. Okay, you got to imagine something and be creative here. Purposeful daydreaming, some people call it, about what is really going on. We're not talking about all the energy we're using. We're talking about only the energy that's taking place that's causing or not causing or causing the energy, the reaction itself not to happen or something else. Something that's going on within those chemicals. Okay? So reaction energy diagram deals with what's happening with the reactants that are changing to some products. That's what we're talking about. Reactants are the things on the left side of the equation. So looking at our water thing a while ago, we're disassociating water into hydrogen gas and oxygen gas. This side over here, these are reactants. This side over here, these are products. You with me? Now, if you don't know that already, what should you be doing? That's a term that you're not familiar with, or terms you're not familiar with. What should you be writing? Writing them down. Okay? You shouldn't have to have me tell you to write them down. You need to know that. Diagrams. I want to change that first G right there should be an A, so I'm going to fix that. Okay. So on the x-axis then, we're going to be looking at, now, I mentioned in the last unit that some graphs actually show independent variable affect independent variable. And when you write titles for graphs, that's the way I want you to write your graphs or your graph titles in the lab. Because in the lab, we're always manipulating some independent variable and causing a change in a dependent variable. We're measuring both of them, okay, but we are actually using an independent dependent variable. What I'm going to show you now is not a true independent dependent variable. It's comparing two different things, but one doesn't necessarily cause the other. You with me? So what we're going to look at down here is the progress of the reaction. Okay, progress of the reaction. This is any kind of chemical reaction here, and we're going to look at one kind of reaction and then another class of reaction. So if this is the progress of the reaction, then on the left side over here we'd have reactants, and over here we're going to have products. Okay? Does that make sense? So when I say progress of the reaction, this works or this works down here because they mean the same thing. But you have to know that, that's what we're talking about here. We're talking about going from reactants to products, and that's what we mean by the products of reaction. I mean, the progress of the reaction. Okay? And since this is a reaction energy diagram, this is the reaction, we need energy over here. Okay? So we're looking at, on the y-axis, the increasing energy as you go up within the system, in the chemicals that are involved in that reaction, not in the stuff around it, not in the container it's happening in, but with the chemicals that we're actually looking at. If we have a chemical reaction happening in water, let's say I have, how many of you ever done the vinegar and baking soda thing? You've done that, right? Okay. Both of those are happening in water. Now you may not realize that, but vinegar is mostly water. It's only 5% acetic acid. So when you mix up the baking soda, which is sodium bicarbonate, you mix it up in there. First thing that happens is the sodium bicarbonate dissolves in the water. So the reaction is taking place in water. But the system doesn't involve any of that water. 95% of the stuff in there is water, but water is not part of that chemical reaction system. Only the baking soda and the acetic acid in the vinegar are the system in that case. You make sense? Now I know that's difficult for you to understand because you can't see it. All right? You got to imagine it. That's where you got to run that movie in your head. You got to be creative, imaginatively creative. Okay? You got to daydream, so to speak, in a purposeful way. All right? All right. Now, there's two classes of these reaction energy diagrams. And one class of reaction energy diagram is a reaction that would be exothermic. Do y'all remember the term exothermic? Okay. So if I'm going to look at an exothermic reaction, what happens in an exothermic reaction? Say what now? Who said energy is released? Very good. That deals with the system. That's what we're looking at. If you were working with a chemical reaction that's exothermic, what would it feel like to you? If energy is being released, how would you know it's really being released? You might feel the heat. If it's giving away electricity, you might get, an electrical charge. Okay? If it's giving away light, you might see the light. Okay? I want you to see the light in a figurative and physical way here. Okay? See the light. Okay. All right. Anyway, if it's an exothermic reaction and energy is being given away, think about this now. If it's an exothermic reaction and energy is being given away, then the ending stuff, the products, must have in them less energy than the beginning stuff. Remember, we can't get rid of energy. In the universe, all energy is conserved. That's one of the thermodynamic laws of the universe. All energy is conserved. Okay? So if we're getting energy out to where we are, if it's feeling warmer, if we're seeing light, if we're getting electricity, then the energy had to come from the system because we're in the surroundings. Remember? Okay? The system is something we can't actually put our hands on so much. The surroundings is where we measure this stuff. Okay? And so we're starting with more energy in the beginning and less energy in the end. Okay? That makes sense? Because this is what's happening in the system. All right? Now, there's a step we got to get from here to here. And it's not a slide. Okay? It doesn't just go downhill. It's more like the beginning of a roller coaster. All right? Before this reaction can happen, you have to get those molecules or atoms, whatever's reacting, to bang into each other at just the right speed and orientation. Otherwise, the reaction doesn't happen. Okay? So there's got to be some added energy to get things started. If I just take two chemicals and put them side by side or put them together, unless the molecules are getting together, there's no reaction. That makes sense? So there's some energy involved in moving things together. Okay? And sometimes it takes a lot of energy, sometimes it doesn't take a lot at all. All right? But whatever it is, that energy's got to go up. Okay? So like the beginning of a roller coaster, we're going to go up, and then finally we're going to go down. Okay? Now I'm simplifying things because some reactions are a bit more complex than this. This is a generalized way of thinking about things, all right? Remember, this is happening in the system where the actual chemicals are, not all that stuff around it, not the water it's taking place in, not the air it's taking place in, not the pot on the stove, not the stove, the kitchen, the house, and so forth, okay? All right. So this is the energy in the reactants. This is the energy in the products. Looking at this graph, what is the change in enthalpy? Looking at this graph, what is the change in enthalpy? Remember, enthalpy is the stored energy in the system. Okay? We talk about heat energy most of the time. Where do I find the change of the energy in the system? Huh? Okay, there is something at the top, but that's not the stored energy in the system. Okay? This is what you have to do to get this reaction started. Huh? Is it the first line? Not exactly, but you're close. And you're kind of close too. Yeah. It's not really the coming down part either. The point in between is really what we're talking about here. Okay, good. I'm pushing you guys and you're figuring it out for yourselves partly. That's the best way to learn. If you're just sitting back and listening, you're not learning very much. But if you're actively involved in trying to figure this stuff out, you're going to do a better job of learning. Okay? I'm trying to make you guys active learners as much as I can. So, the difference between the amount of energy we have at the end and the amount of energy we have in the beginning, that's the change in enthalpy. Okay? In this case, the change in enthalpy is it positive or negative? It's going down, so is it positive or negative? It's negative. That makes sense? If the energy is greater at the top, at the beginning, and less at the end, then delta H, the amount of energy in the system is being reduced. Okay? Now, somebody mentioned the top of the hill here. We do call that something right there, but that amount of energy from the amount you start with to what you have to get it started, because the roller coaster doesn't start till you go over that first hill, right? Okay? This is called activation energy. We activate the reaction. That's activation energy. And technically, there is something called an activated complex when you get here. That is to say, whatever the reactants are, they bang into each other, and that very, very temporary orientation when they bang into each other, that's called the activated complex that exists right there. Okay, so there is an activated complex. You can't really call it a compound because a compound kind of sticks together. So an activated complex exists when you get there to that top of that hill, okay? An activated complex exists here. All right, are you beginning to kind of get an idea of what we're talking about here? Now, this is all theory, because we can't touch energy. We can't see it. We can't actually show that it's happening. When we can't measure energy directly, we have to measure change in temperature or something else and then calculate the energy. All right? That's an exothermic reaction. Okay? What's the other kind of reaction if you compare? Endothermic. Let's look at an endothermic reaction then. So again, this is a reaction energy diagram. So this is a reaction energy diagram for an endothermic reaction. And what happens with an endothermic reaction? It what? It absorbs energy. Exothermic gives away energy. Endothermic absorbs energy. But what's happening with our graph is what's happening in the system. The energy that we see is happening in the surroundings. Okay? So for us, an endothermic reaction, the system's losing energy, but it looks like us is giving away energy. So it's warmer, we see light, or we see electricity, or we get electricity as a result. With an endothermic reaction, it's taking in energy. The products are going to have more energy than the reactants did. Okay, so we got the progress of the reaction again down here. And then we have reactants on this side. We got products over here. Okay, and again we got energy in energy as we go on the vertical axis over here. Okay. All right. So if this is endothermic, it's taking in energy, then the products have to have more energy than the reactants. So here's the reactant energy, here's the product energy. Okay? You still have to have some energy to make the system get started. Just because I put reactants together won't make them react unless they do something to bang into each other with enough force in the right orientation. Okay? If you're a football player and you want to stop, and you're a defensive linebacker and you want to stop a running back, you don't just back into him, do you? Huh? Yeah. You want to stick him. Okay, that's one way to put it. All right? So you got to hit him heads up, okay, shoulders forward, and wrap him up, right? And get his feet off the ground and drive him in the ground. That's what you want to do. That's the right orientation to stop a running back. Yes? Yeah? Okay. So just because these reactants bang into each other doesn't mean it's going to happen. It's got to have the right orientation. Because if you just back into a running back, he's going to bounce off and go somewhere else. All right? So we still have to have some kind of activation energy. And we've got to have the right orientation. And if you have that, then it goes up, and then it goes over the hill. All right? And again, there's an activated complex at the top. Or an activated complex exists when you get there. It doesn't mean that that is the activated complex. Please understand that this top of the hill is not the activated complex. There is an activated complex when the activation energy gets to that. That's all I'm saying. Okay? An activated complex will exist when you are there. All right? Okay. Now, again, we're starting down here. We're ending up here. So there is a change in the amount of energy stored in the system. And what do we call the change of the energy stored in the system? Huh? Enthalpy. Okay. So is the enthalpy going to be positive, or change in enthalpy going to be positive or negative? Positive. Because it's going up. Okay? So in our exothermic reaction, we're losing energy in the system. This is negative. In our endothermic system, the delta H is positive because it's increasing. We're increasing the amount of energy stored in the products actually over the reactants. Okay? We still have an activated energy, we have activation energy, and that's from the beginning energy to wherever we are at the top of that hill. Okay? So that's I put activate energy. That should be activation energy. I just realized I misspelled that a while ago. Activation energy here. This is also activation energy here. All right? Everybody got that? Yes, no, maybe.
So,
All right. Somebody tell me what a catalyst is. What? Slows the reaction? Actually, something that slows the reaction is called an inhibitor. Okay? What does a catalyst do? Speeds up the reaction. Okay? So let's go back here and look at this for a minute. All right. The part of this process that slows down the reaction, since you mentioned that, is the activation energy hill here. Okay? The larger this hill, the less of the reactants can become products. We talked about diamonds a while ago. The reason that even though diamonds are, they actually give away energy when they decay into graphite, they actually are exothermic like this. The reason that diamonds almost never decay, I shouldn't say never decay because, I mean, while it is going to happen in our lifetimes, nobody's ever going to see it. It actually is happening, okay? But the thing is, the activation energy hill is so huge that nobody can get over it. Does that make sense? You with me? I mean, just think about that. If you're that little engine that could, right? Remember that story? Little engine that could, I think I can, right? Go over the hill, all right? Well, if that little engine that could runs out of coal to run the steam engine or runs out of fuel before it gets to the top of the hill, it ain't going over that hill, right? Using ain't, which we shouldn't be using, but that's okay. All right? It's not going over the hill. So if the activation energy is too high, we're not going to get there. All right? Whether it's exothermic or endothermic, it doesn't matter. If the activation energy is too high, we're not going to get over here. You with me? Well, here's what a catalyst does. A catalyst takes and shaves off the top of that activation energy hill. You see that? It gives you a new pathway, we call it, for the reaction to occur. Okay? That makes the activation energy hill lower. All right? Now, if we want to slow down the reaction, somebody mentioned this a while ago, if we actually want to slow down the reaction, then we add something to the reactant system that will increase the energy hill, and we call that an inhibitor. You got that? Now, having said all of that, this is a really super simple simplification of this process. Okay? There's way more to this story than we covered today. And when you get to college and take chemistry, you'll probably cover some of those way more things. But for right now, this is as far as we go in high school chemistry. The beginnings of understanding this idea, these theories. Okay? This is the stuff that you need to know. Got it? Now, I want to give you 2 homework problems that go along with what we did today. Okay? And one homework problem is I want you to draw an activation energy diagram that includes a catalyst pathway for an endothermic reaction. I showed you the one for exothermic. You're going to do the one for endothermic. Okay? So I showed you an endothermic reaction with no catalyst pathway. You're going to create that for homework. Okay? And it shouldn't be hard, but you need to label everything, okay? Everything needs to be labeled on there. Because you know what? The more times you label things, the more likely you ought to remember it. When the time comes, you got to use it. Okay? Label. Let's just make it easy. everything. All right? And number 2. The Gibbs free energy equation it's okay to predict All right, now here's the reaction we're talking about. Here's nitrogen. Here's hydrogen. And this is ammonia. Okay? Let's see, to balance this we need 2 of these and 3 of these. And, well, I'll just leave it at that. I'll let you guys figure out when it's going to be spontaneous, basically, using the Gibbs free energy equation for your argument. Okay?